Okay, this video has application to the central limit theorem, which is mainly section 8.1 in your textbook. Finding the mean and the standard deviation of the sample and distribution of the means. If we give you the original population of adult cats that has an average weight, a mean of 10 pounds and a standard deviation 1.5 pounds, and we collect random samples of 40 cats each are taken from the population, what's the mean of the sample means? If you watch the applet, you notice the mean of the sample means will be the same as the original mean, which is 10. And you also notice that the standard deviation of the sample means, which is called the standard error of the mean, shrink, and the curve will become narrower. And the formula for the new standard deviation, which is called sigma of x bar stands for sample means. Will be the original population standard deviation divided by the square root of the sample size, which is 40 in our case. So we have 1.5 divided by square root of 40, which is 0.237. Let's do another one. The average height of adult women in a country is 65 inches with a standard deviation of 3.5. Using the central limit theorem, calculate the probability that the average height of a sample of 32 women. Now remember, guys, look, it's giving you a sample. So once he gives you a sample, the question is going to be about the sample mean. What is the probability that the average height, which is the mean of a sample of 32, is more than 66? So it's not about x greater than 66. It's x bar, which is the sample mean greater than 66. Remember, the mean will remain the same as the mean, so we don't change that. So the mean, we're going to use 65. But for the standard deviation, we're going to be using 3.5 divided by square root of 32. That's very, very important before we go to the applet normal calculator. What is 3.5 divided by square root of 32? So mean is 65. And 3.5 divided by square root of 32, I got 0.67. And we need the probability of x bar greater than 66. Compute. We use x when it is about one individual. We use x bar when it is about the sample. So that would be the answer. I made a mistake, should be 0.62, not 0.60. When you take 3.5 divided by square root of 32 is 0.62. And the answer will be 0.0534. You can see the answer right there. And this is how we write it down. Probability of x bar greater than 66 is 0.0534. And if you want to write it as a percent, you can do that. Or what? 5.34%. Comparing distributions. A teacher grades two sets of exams. The scores of the first set follow a normal distribution with the mean of 75 and a standard deviation of 11. And the scores of the second set follow a normal distribution with the mean of 70 and a standard deviation of 12. Without calculating any probability, discuss which sets of scores is more likely to have a score of 85. Okay, so in which set? In the first one or in the second one? You can see for the first one, if you add one standard deviation to the mean, it will be 86. So 85 fall within one standard deviation of the mean. But if you look at the second set and add one standard deviation, it's going to be 82, and 85 does not fall within one standard deviation of the mean. It falls within two standard deviation of the mean. The closer to the mean is the more likely this to happen. So it means that it is more likely to have a score of 85 in the first set. Real world applications. Consider a manufacturing process that produces light bulbs with a lifespan that follow a normal distribution. The mean lifespan of light bulbs is 800 days and the standard deviation is 50. A quality control inspector randomly select 33 bulbs. So this is n, guys, equals 33. Yeah, so we have a sample size for test. What's the probability that the mean lifespan of this sample exceeds 810? So he wants a probability of x bar greater than 810. We're going to be using the normal calculator, but remember, we'll be using 800, but instead of 50, we have to use 50 divided by square root of 33. Let me take you to static run. So the mean is 800. If you divide 50 by square root of 33, you get 8.7, and we need x bar greater than 810, and that's the answer, 1252. I'll take you back, and it is 1252. How does the central limit theorem justify your calculation? He didn't say that the original population was normally distributed, but he gave me a sample size which is 33, which is bigger than 30. If the sample size is large enough, means bigger than 30, it doesn't matter whether the original population is bell-shaped or not bell-shaped, so we are okay to use the central limit theorem. Okay. Explain some review now for everything that has to do with the normal probability distribution. Explain what a normal distribution is. Normal distribution, also known as the Gaussian distribution, is the probability distribution that's symmetric about the mean, showing that data near the mean are more frequent in occurrence than data that far from the mean. The normal distribution appears as a bell curve when graphed, bell-shaped curve. Calculating probabilities. Given a normal distribution with a mean of 105 and a standard deviation is 13. So 105 and a standard deviation of 13. What's the question? What is the probability that a randomly selected score from the distribution is between 87 and 110? This is how we write it down, guys. 87 less, probability of 87 less than x less than 110 equal, and you can see I put the answer there, but I'm going to show you how to do it. So 87 and 110. So just go between, put 87 here, put 110 there, compute, and it's 0.5667. Okay, that would be the answer. That's what we have. The weights of bags of apples are normally distributed with a mean of 50 and standard deviation of 2. So let's do 50 and standard deviation of 2. Let's go back. What's the minimum weight of a bag of apple that falls within the top 5%? Top 5% means the heaviest, the top 5% heaviest weights. So it's going to be an area to the right. So we're just going to go to StatCrunch. Okay, since now he gives me the area and he wants x, so this is gonna go blank right here, and 5% is gonna be right there. And guys, watch, you're gonna see the answer appears right here, 53.3 pounds. Okay, so that's what I put. The scores on a university entrance exams are normally distributed with a mean of 525 and standard deviation of 85. So 525, standard deviation of 85, and let's go back and see what the question is. Determine the score that separates the bottom 10% from all scores from the rest. Bottom 10%, guys, means it's an area to the left. So he's giving me an area to the left. So when I go back to StatCrunch, rather than greater than, I have to use less than. And my area here is going to be a 10%. And it's going to give you the x value right there, 416. Okay, so x is 416. I put 516 here, should be 416. Okay, now the last exercise that covers everything that has to do with normal probability distribution. Suppose that the weights of navel oranges is normally distributed with a mean of 8 and standard deviation of 1.25. So let me just change that to 8.25. What is the probability? What proportion of oranges weigh more than 9.5 ounces? Meaning, if you select one orange at random, what's the probability that its weight is more than 1.95? So we need probability of x greater than 9.5. There you go. Greater 9.5 right here. And here's the answer, 1151. Next question. What proportion of oranges weigh less than 8.7 ounces? So we want the probability of x less than 8.7. It just take you back, change that to less, 8.7. Compute 7123. Next question. What proportion of oranges weigh between 8.25 and 10.75? So need between now 8.25 and 10.75. Compute 4068. And that's the answer. And this is how you write it down. And let's see what next. Find the 80th percentile of the distribution of weights of oranges. You can say find the value of x below which you find the lightest 80% of all oranges. 80th percentile, as I stated in other videos, it's an area to the left. So you have the area to the left and you need the x value. You put the 80, okay, we need back standard. You put the 80% right here. And now, guys, you're going to get the value right here, the x value, which is 9.05. So x is 9.05. Now the central limit theorem, because we have samples. If 9 oranges were randomly selected, what's the probability that their mean weight is less than 9.5? So we need a probability of x bar less than 9.5. And we have 9 oranges. Remember, we'll be using the same mean, which is right here, 8. But the standard deviation has to be 1.25 divided by square root of 9. They cannot use 1.25. So 1.25 divided by square root of 9 will be, guys, 0.42. And we need a probability of, I forgot, x bar less than 9.5. Which is 0.9998, so almost the entire curve. Okay, so that's the answer. If 36 oranges are randomly selected, what's the probability that their mean weight is more than 8.2? So we need a probability of x bar greater than 8.2. And watch, guys. Remember, the standard deviation is going to be now 1.25 divided by square root of 36, which is 0.21. Greater than x bar 8.2 and 1705. There you go. And the last question, what would be the minimum weight of an orange that places it in top 10%? Top 10%, guys, means area to the right. So we need x and we have the probability. So just go there. Back to 1.25 now after we're done with this. Okay, greater than, and the 10% will be right here, and that's 0.9.6. If I say top 10%, you just put 0.20 here, and then you can get the answer. So that's going to be 9.6. That concludes this video.